So guys, here we go. Again, you've got everything that you need in front of you. You are going to need your equation sheets and maybe, you might want to grab your calculators. I would grab those as well, just to make sure you remember how to fiddle with logarithms in your calculators. So guys, again, just to be clear, if you have the experience, hey, this is familiar, that's good. If you have the experience, not all of this is familiar, that's expected. We'll obviously highlight the stuff that we haven't talked about in days or weeks, years previous, but we're going to dig in. You okay? Equation sheet? You got it. All right. So guys, let's talk fundamentals. You right? So 16 and 17 are all about acids and bases. We're going to bring equilibrium into this, but guys, today is the fundamentals. So you ready? Fundamentally, let's think, what do acids do? Give away hydrogens. Guys, fundamentally, what do bases do? Now we've got a problem. Fundamentally, what do bases do? And the answer is actually two different answers. They're similar, they're complementary, but they're not the same. I'm going to throw it up in the notes in just a minute, but I want to talk about it now so that you can underline the important bits. So guys, when we talk about what acids do, we're going to use different verbiage. We're going to say hydrogens, we're going to say protons. Those are the same thing. But when we talk about what bases do, it's not always about hydrogen. So guys, sometimes we think of bases as being things that give away hydroxide. Let that sink into what you understand about bases. Guys, what are the substances that you know to be bases, the strong bases? You wrote them down. Remember, you memorized them this summer. What are the bases? So the group 1 and heavy group 2 hydroxides. Doesn't that make sense? Guys, the things that we already know to be bases are the group 1 and heavy group 2 hydroxides, fitting with the idea that bases give away hydroxides. Now guys, everything that we just talked about is what is called the Arrhenius definition of bases and acids. So I would encourage you to circle hydrogen ions. I would encourage you to circle hydroxide ions. Because guys, in the Arrhenius definition of acids and bases, that's what they do. Acids give away hydrogen ions, bases give away hydroxide ions, and that makes sense given what we understand. Now, guys, understand this definition is good, but it's limiting. The reason that it's limiting is because we've got, This is actually going to be a big enough problem that I think I'm going to have to start I can't fake this, so I'm going to have to, I don't know how far back I'm going to have to go, but let's see what happens here. So if I restart this and then do this, okay, now I'm drawing, so that's good. So now let's see what happens here. Okay, now can I write? Okay, so I can write there. Now let's see if I can write. Okay, I'm back. Okay, so guys, so the thought then becomes this. In the Arrhenius definition, acids give away hydrogen ions, bases give away hydroxide ions. By the way, when those react together, what do they form? Water, right? Neutralization reactions. You've got a hydrogen, you've got a hydroxide. Those come together and make water. Now, guys, this works really, really well until we have to start having conversations about things like ammonia. Because ammonia is a base. But ammonia ain't got any hydroxide. So guys, now what we have to do is step out of the Arrhenius definition of acids and bases and bring in Bronsted-Lowry. Guys, Bronsted-Lowry is actually the acid-base definition that most of you will use for most of your chemical career. Guys, understand that if you really get into chemistry, we're not going to talk about it, but there is a day that's coming when you're going to darken this door and take organic chemistry. When you get into OChem, they will introduce you to another definition of acids and bases that doesn't have anything to do with hydrogens and hydroxides. It actually has to do with electrons. Not surprisingly, it's the Lewis definition of acids and bases, because Lewis dot structures, Lewis was an electron guy. Don't worry, did you pick that up in chapter 16? Don't worry about it. It's not part of the AP curriculum. So, thinking about the Bronsted-Lowry definition, guys, I would encourage you to start drawing some arrows. Ready? This is the Bronsted-Lowry definition of an acid. How does that connect to the Arrhenius definition? Because they're actually protons are, oh gosh, guys, protons are hydrogen ions. I think that's an arrow worth drawing. Guys, protons, do we need to talk more about that, or is that okay? Hydrogen atoms, one proton, one electron, make it an ion, take away the electron, you're left with a proton. Okay, so guys, this is where things change. In the Bronsted-Lowry sense, we don't define a base by what it gives away, we define it by what it takes in. And so in the Bronsted-Lowry sense, bases do not give away hydrogens, or bases do not give away hydroxides, they take in protons. But now, you ready for the $10,000 thought? That's actually still the same as the Arrhenius definition. Can you connect the dots? Go ahead. But and you're right, but how can that be? How can something increase the concentration of hydroxide if it doesn't contain any? Okay, and that's the trick. Guys, this is the thought. You may want to write this down even though it's not explicitly there. Guys, all of this is understood to be in the context of water. And this is one of the things that makes acid-base chemistry really complicated. Because guys, when we talk about aqueous chemistry, the water is just like a playground where the ions get together and do chemistry. Right? Precipitation reactions, things like that. You dissolve things in water, you react them together. Guys, the problem is this. In acid-base chemistry, the water is no longer a bystander. The water gets involved in the game. And that's actually what's going on here. You may want to write this down. So what happens is NH3 is in water. Guys, all of the acid-base chemistry that we're going to talk about happens in water. And so the idea then becomes this. NH3 is a base. By the Bronsted-Lowry definition, what's it going to do? Take a hydrogen away from where? The water. And when it does, we end up with ammonium and hydroxide. And there's the hydroxide that identifies this solution now as a base. That then ties back to the Arrhenius definition that says that's what bases do. So guys, fundamentally then the idea is this. When we talk about Arrhenius acids and bases, we limit this conversation to the strong acids and bases, because all of the strong acids and bases fit in the Arrhenius definition. In order to talk about Bronsted-Lowry, that allows us to then bring in the idea of the weak acids and bases, and because it allows us to understand bases as forming hydroxides by taking hydrogens away from water. Does that sit okay? Thoughts or questions about that? You okay? You all right? Good to go? Okay. And so guys, then you'll notice in the notes, it does mention a little bit about this, the idea that the majority of our study is going to be understanding acids and bases in the Bronsted-Lowry sense, but understand that Arrhenius thing is out there, and there's also a Lewis definition that you guys don't need to worry about. You guys okay? Yeah. I wouldn't spend time on it. You never know, but it's certainly not an important enough idea that I wouldn't worry about it. Okay, so guys, with that said, then where are we headed? Well, now that we have these general senses of what acids and bases are, guys, what we're going to do is we need to understand. We're going to talk about acids, and this is going to be familiar, and we're going to talk about this idea that all acid-base chemistry happens in water. Now, we've already talked about that here. When you dissolve strong bases in water, they give away hydroxide. Strong acids give away hydrogens. We now understand that weak bases can take hydrogens from water, making hydroxide. But guys, we're going to talk about what do acids do in water. And you learned this last year, but let's talk about it. This is all about a thing called hydronium ion. So guys, again, the idea is that when we talk acid-base chemistry, it's always in the context of water. And so when we take something like an acid, and guys, remember, acids give away protons, those protons interact with water. Can you see how this is going to happen? It's kind of like crazy hydrogen bonding. So guys, this is a proton, right? You okay with that idea? This is a proton, wildly positive. Now we've got these unshared electrons on the oxygen that are regions of high negative electrical charge. The proton globs onto one of those electron pairs, and it literally forms a third covalent bond, forming this ion called hydronium. Notice that it's got a positive charge. Do you remember this from last year? So guys, these are the things you need to know about hydronium. Guys, hydronium ion is actually the thing that gives acids their characteristic properties. So if you spill acid on your arm and you're like, the acid's burning me. No, it's not. It's actually the hydronium ion that is attacking your flesh. Because guys, no matter what acid you put in water, all that acid does is gives hydrogen to water and forms hydronium ion. And it doesn't matter what the acid is, that's all you're doing is forming hydronium ion. So guys, when we talk about, though, hydronium ion, and I would encourage you to circle this stuff, guys, when we talk about hydronium ion in this whole process, we are going to represent this in one of two ways. So the thought then goes like this. What do acids do when they go in water? Well, the answer could be they form hydrogen ion. The other answer could be they form, my board's really being crazy. The other answer could be they form hydronium ion. And guys, the trick here is that this is interchangeable. What you're going to find throughout this unit is sometimes we're going to think of acids as being hydrogen ion producers. Sometimes we're going to think of them as being hydronium ion producers. But guys, in the back of our mind, we understand those are the same thing. Go ahead. Exactly, and that's the point, that sometimes we're going to say that pH is the concentration of this. Sometimes we're going to say pH is the concentration of that, but it's truly the same thing. Guys, do you understand how that's the same? Would it be helpful to show you, or can I show you? Let me just do this quickly. So this is the idea. And if you need examples, write this down. Hydrochloric acid. Strong or weak? Strong. What does it do in water? Dissociates into hydrogens and chlorides. Write it down with me. So guys, it does that. What does it mean that this is a strong acid? Let's talk about that quickly. What does that mean? Does that completely, right? Completely breaks apart. So can you now see that acids produce hydrogen ion? Is that okay? Now, guys, do this in your brain. Where does this happen? In water. So now, let's respect the fact that the only place that this happens is in water. Let's now include the water in the conversation. Well, if that's now including water, when HCl gives away a hydrogen, where does it go? To the water. And it forms H3O plus and chloride ion. So guys, there's your H3O plus. So the idea then is this. If we think of an acid in the context of water, we think of hydronium ion concentration. If we think of an acid but don't include the water, we think of hydrogen ion concentration. But all the while, we realize there has to be water present for this to take place. It just isn't always necessary to include it in the chemistry. Do you see now the difference? Same ideas, but different, yeah.
What if water were to like steal hydrogen?
It does. That's what we're about to do. Yeah, it's actually called the autoionization of water. You're about to have an interesting thought. So, go ahead, Jeanette. Yeah, that's a really, really good question. So, let me just babble for a second. Did you hear Jeanette's question? Why does water, and you can think of it as giving or taking, why does water take the hydrogen from the acid? Or why does the acid give the hydrogen to water? You understand the question? And guys, this is what I was alluding to earlier. And this, at first, you'll get used to it. But guys, at first, that very idea is what makes acid-base chemistry difficult. The question is really, how do we think about water, which we used to just think of as an environment, right? You dissolve salts in water, you dump them together. Water, it wasn't even a spectator. We didn't even talk about it. But guys, now we have to talk about the water. So Jeanette's question, how did you say it? Giving or taking? Taking. So why does water take the hydrogen from the acid HCl? You understand the question? I'm going to turn it to you as a question. What does it mean to be an acid? Why is HCl an acid? What makes it an acid? It gives away hydrogens, right? But what you're going to find out as we get deeper into this is the answer is more complicated than that. So what about this? Guys, if that's true, then why isn't NH3 an acid? It has hydrogen. So now we need to ask a bigger question. Why does HCl give a hydrogen to water, but why does NH3 not give a hydrogen to water? Why does NH3 take a hydrogen from water? And guys, the answer is this. Molecules, and we're not going to get into this too deeply, but molecules have an affinity for hydrogen. And it turns out that when we say something is an acid, what we're actually saying is it's more acidic than water. And when we say something is a base, what we're saying is it's less acidic than water. So guys, check this out. You could even write this down if you want, but it goes like this. Guys, water is in the middle. If you want to write this down, you can. Water is in the middle. Is water an acid or is water a base? Yes, it's both. Guys, water is hydrogen hydroxide. Water is both an acid and a base. So let's do this. Let's put our acids up here and let's put our bases down here. So guys, the idea is this. HCl, HNO3, HF, well, HI, HBr, all these things that we know to be acids. All that it means to be an acid is that it's better at giving away hydrogens than water. Water has an affinity for hydrogen. And if you are an acid, all that it means is these things are better at giving away hydrogens than water is. Water is the point of reference. So if you're an acid, you give away hydrogens better than water does. So what if you're a base? What does that mean? Well, if you're a base, that means let's put NH3 down here. Guys, if you're a base, that means that you're better at taking away hydrogens than water is. So the point of reference is water, and anything that's an acid, water will take hydrogens from. Anything that is a base, water will give hydrogens to. Yeah. Can I just mention one more thing? Guys, if you're wondering why, we're going to spend an entire day in about 3 days and talk about it. We're going to talk about why do some things give away hydrogens and why do others take them in. We're going to look at structure and function, but we're not going to do it today. Yeah. Yeah. What? Oh, okay, yeah. And so I haven't populated the calendar yet, but there's going to be a whole day on structure. And it's really fat. It gets even worse than that because we're going to ask this question. Why is this a base? Why is this an alcohol? Why is this an acid? And why is that neutral? They all contain hydrogens. Why do they function differently? And we're going to dig into structure and talk about it. So, Jeanette, did that answer your question at least as much as we can right now? You guys okay? Okay, so guys, where I am then is I think we're okay with this idea of hydronium ion. All acid-base chemistry happens in water. If we're thinking about acids, acids give hydrogen to water. That forms hydronium ion. That is the active ingredient in an acid. And as Alyssa mentioned, that's also the thing that we measure concentration of when we're talking about pH. Are we all up to speed there? A lot of that was review, I know, but are we okay? You're good? Can I go on? Okay, all right. So now, guys, moving on. What we need to do now, and this is also a review from last year, we now need to talk about conjugates. So, guys, this is the idea. Bronsted-Lowry. Guys, put on your Bronsted-Lowry hat. What does Bronsted-Lowry say acids do? Gives away protons, proteins. Guys, acids give away protons. What do bases do? Yeah, guys, watch. So acids give away protons, bases take them in. So when an acid and a base get together, what happens? The acid gives away a proton. Where's it go? To the base. And guys, in the Bronsted-Lowry sense, that's all an acid-base reaction is a handing off of protons. And because that's the case, we can then talk about things called conjugates. I would encourage you to draw these arrows. So guys, what does an acid do? Loses a hydrogen. When it does, it becomes the conjugate base. Where does the hydrogen go? To the base, and when it does, it then becomes the conjugate acid. Now, guys, the thought is this, and we talked about it briefly last year, but I think you're better prepared to understand it now. Now, guys, do this. Ignore the acid in the base, and then think about the conjugates. So, guys, what does it mean to be a conjugate acid and a conjugate base? Are they really acids and bases? Yes. And they do chemistry just like acids and bases. Think about it this way. What does an acid do? Gives away a hydrogen. Where does it go? When the acid loses a hydrogen, it becomes the conjugate base. And when the base gains the hydrogen, it becomes the conjugate acid. So guys, let's focus on the base first. So the base picks up a hydrogen, right? So now whatever this is, it's got an extra hydrogen compared to this. Guys, that extra hydrogen allows this to function as an acid. Do you see that connection? Now, guys, go to the acid. What does the acid do to become the conjugate base? It loses a hydrogen. So now we've got this thing over here that's the conjugate base, but now this guy's missing a hydrogen. And sometimes it would like it back. And when it gets it back, it's now functioning as a base. So guys, these conjugate acids and bases are very much acids and very much bases, and they function that way. And so we're going to spend multiple days in the next month talking about the chemistry of conjugates. Yeah.
So does anything ever neutralize if it is not conjugate?
That's a really good question, and we're going to talk about it. Let's do it now. I wasn't planning on doing this. Guys, please don't write this down. This doesn't belong in your notes right now. But the heart of Susanna's question is really important. She's like, does anything really then neutralize? And guys, let me show you this. I'm going to take a little different tact on your question. So guys, let's include the water. It'll be helpful. What's the conjugate base?
Oh, Cl minus.
Cl minus. Guys, good for you. Guys, that very skill is critical. So let me try it again, and I know you know the answer, but you've got to be able to quickly identify conjugates. So the answer is, what's the conjugate base? And the answer is chloride. How did we know? Well, we know that HCl is an acid, and we see the HCl losing a hydrogen to water, forming hydronium, forming chloride ion. Guys, to find your conjugate base, go to the acid, take away a hydrogen, what's left is the conjugate base. Does that make sense? Now watch this. This is vinegar. When vinegar is dissolved in water, by the way, guys, this is interesting. All of the strong acids, before they dissolve in water, are gases. Did you know that? And all of the weak acids, before they dissolve in water, are crystals. They look like sugar. So all of the strong acids are gases. I used to have a tank of HCl gas. They took it from me. But you could bubble it through water and make hydrochloric acid. All of the weak acids, I have vinegar as it's solid. But all of the weak acids are crystalline solids. Anyway, all of that to say this is an acid, and it also forms this and then this. So guys, in this reaction, what's your conjugate base? Acetate, right? The thing at the end. So again, here's your acid. Take away the hydrogen conjugate base. Good? Does that make sense? Okay. Now, guys, here's the question. Look at the second reaction. What's wrong with it? Do you see it? That's it. It's a weak acid. Some of you are going, how are we supposed to know that? Because you memorized the 7 strong acids. And guys, remember, strong doesn't mean deadly and dangerous. They are, but guys, strong means completely breaks apart. So the 7 strong acids break apart completely. Any of the other acids, which are by definition weak, reach equilibrium. Does that make sense? Because here's the question. Guys, why is HCl a strong acid and why is acetic acid a weak acid? You ready for the interesting answer? It's because of the conjugate base. The idea is this. Guys, chloride, I'm going to just use the word. Guys, chloride is a worthless base. The book uses the term of negligible strength. It's worthless. Guys, chloride is such a weak and worthless base that it cannot steal a hydrogen back from hydronium ion, therefore it can't drive the reaction in the other direction. That is not true of acetic acid. Acetate is actually a pretty darn good base. As a result, acetate ion is able to pull hydrogens off of hydronium ion and drive the reaction in the other direction. So guys, the big idea is this. What makes an acid a strong acid? And the answer is the conjugate base is worthless. What makes a weak acid is that the conjugate base is actually basic and it does pull hydrogens off of hydronium and drives the reaction backwards as well. Does that make sense? So that's really the underlying thought behind your question, is that anytime you've got a strong acid or a strong base, they will completely break apart. Anytime you've got a weak acid or base, they will reach equilibrium. So now, what if you react them together? And the answer is, anytime you've got a strong component, whether it's a strong acid or a strong base, it destroys the equilibrium, and those will always go to completion. Those neutralize. And that is this chemistry. That's, guys, what we were talking about in lab last time is this, that acetic acid does break apart into these ions, but when you dump sodium hydroxide into it, the sodium hydroxide rips the acetic acid apart and drives this reaction to equilibrium. I'm so glad I didn't erase this. Drives this to completion, and it no longer allows the acetic acid to reach equilibrium because this gets destroyed as quick as it gets replaced. And that's exactly what we're talking about. So guys, do you understand this idea about the strength of conjugates and therefore strong and weak acids and bases? Is that okay? So guys, going back to the notes then, I think we're good on that whole page on conjugates. Is that okay? Okay. So now guys, we're going to go where Alyssa's brain took us just a moment ago. And we're now ready to talk a little bit about the relative strengths of acids and bases. In addition to that, this final thought off to the left. So guys, when we talk about the strengths of acids and bases, what we're talking about is strong and weak. And we understand again that it doesn't mean scary or dangerous. It means does it break apart completely? So guys, we've got strong acids and they completely transfer their hydrogens to water. And those are just the big 7. Then guys, we've got weak acids and those things only partially ionize. Instead, they reach equilibrium. Now guys, this down here is actually just a retelling of this. This idea that strong acids have worthless conjugate bases and weak acids have stronger conjugate bases. That is this thought right here. The stronger the acid, the weaker the conjugate base. So there's an inverse relationship between these. So the extreme is strong acid is a worthless conjugate base, but as that acid becomes weaker and weaker and weaker, its conjugate base becomes stronger and stronger and stronger. And guys, that's actually what is then brought out in this. I would encourage you to circle. Let me get in circle mode. I'm going to pick a color that's disgusting but will stand out better against the background. So guys, do you see the word there? Negligible. I don't like it. You like green? You like green? Green's actually my favorite color. I don't know. It just doesn't. See, I had a green water bottle and I lost it. And then no. That's a gross green. No. I actually had a guy from Cannondale Garmin throw this to me during the tour of Utah. I felt like an idiot. I was standing by the road up by Pineview Reservoir cheering as the tour went by. I was the only guy ringing a cowbell. And I think the guy felt bad for me, so he hucked me a full bottle, which they typically don't do because they need the fluid. He threw this to me full because he knew I was an idiot. So, not this. Okay, so guys, back to the... Don't miss the chemistry. Guys, it goes like this. I would encourage you to write this down. So guys, here's our acid, here's our base, our conjugate base. But guys, notice that these 3 acids, we can talk about all 3 of them, those 3 acids are strong. Guys, what in that diagram says strong differently? 100% ionization. That's our strong. But notice what that means. If these are strong, these are worthless. Or, in more politically correct terms, of negligible strength. But then, guys, notice what happens. As we move down this list, guys, you'll notice that we get into the weak acids. They don't completely ionize. And guys, as this happens, as the acid gets weaker, the conjugate base actually gets stronger. But then, guys, did you notice this? There's our 0 points. When we talked about this idea of what does it mean to be a strong acid? It means stronger than water. What does it mean to be a strong base? It means stronger than water. So guys, understand the weak acids and bases are the blurry part in between. But guys, when we say strong acid, we mean it's better at giving away hydrogen than water. And when we say a strong base, it's better at taking in hydrogen than water. So our 0 points are water, and then depending on if it's an acid or a base, the conjugates thereof. So our frames of reference for water And then, guys, and so why is water our frame of reference? Because all of this chemistry happens in water. And so when we say that it ionizes 100%, it means 100% of it gives away its hydrogens to water because it's better at it than water. And so we need to get comfortable with this idea of water being a part of the process. So how are we doing on these relationships?
So are all the bases past water?
Yes. Sides of the group 1 and group 2 salts. Those are strong bases, but that list is not exhaustive. As you can see, there are other strong bases. And so here, I'm still in writing mode. So there's your hydroxide, right? That's the first of the strong bases, sodium hydroxide, on and on. But then there are others. But these are things that are strong bases, like an O2 ion, and actually a negative hydrogen ion, and then a CH3 ion. Those are things that you don't run into much in inorganic chemistry, the chemistry that we do in this class. When you get into organic chemistry, these become important species, but we don't talk about them much in this class, so we don't include them in the list. You won't see those on the AP test. Okay, you guys good? But I should say this, this list is exhaustive. I shouldn't say, no, there are a couple, never mind. It's exhaustive for us. Go ahead.
So with the 3 strong bases that it shows, is HCl
Do you mean strong bases or strong acids?
is it considered like
Oh, I see. No. So let's talk about that. So we know strong means complete, right? And you can't get more complete than complete. Do you know what I'm saying? So in that sense, all 7 of the acids are equally strong. With that said, there's 2 other things to think about. One of them is this. Sulfuric acid is the only strong acid that's polyprotic. The other 6 are single H's. Sulfuric acid has 2 H's. You're going to find out, we'll talk about this when we talk about polyprotic acids. It gives away the first hydrogen completely and then the second hydrogen partially. But the fact that it does have an additional hydrogen to give away means at any particular molarity, the hydrogen ion concentration will be higher than any of the other strong acids because it's got that bonus hydrogen. The other thing to think about, though, is you said, are they all equally strong? Let's not use the word strong correctly, and let's talk about, are they all equally corrosive? And in that sense, the answer is definitely not, because it turns out that while the conjugate bases of these things are worthless bases, they can be wildly reactive. You shouldn't admit this out loud, but have you guys seen Breaking Bad? Don't admit it. But guys, there's this scene in Breaking, you know the story, right? Walter's a chemistry teacher, cancer, needs money, deals drugs. It gets ugly. But there was this scene where they killed what was his little friend's name? What was it? Jesse. And so Jesse was tasked with getting rid of the body. Do you remember this? And so the answer was fill up a bathtub with hydrofluoric acid. Remember, he's a chemistry teacher. Throw the body in, and the hydrofluoric acid actually would eat the body. It would be gone. It's gone. But the thing that's interesting, guys, is hydrofluoric acid is actually a weak acid. It's not one of the big 7, but it's crazy corrosive, not just because of the hydrogen, but because of the fluorine, right? And then actually things went really bad because Walter told Jesse to put the acid in a plastic bathtub. He put it in a cast iron bathtub, and it actually ate a hole through the bathtub, and body goop fell through the roof. Anyway, you guys haven't? Okay, never mind. All right. So, guys, you okay with the idea? We're good on these? All right. So now zooming out and moving along, we're going to talk about Luke's interesting question. So are we okay with conjugates and stuff? We're good with conjugates. So do you guys remember amphoteric? Let me show you quickly. So guys, quick concept. So the idea is this. Here we've got HNO3. Here we've got water. Notice here the water takes in the hydrogen, forms H3O. Here we've got H2O losing a hydrogen to ammonia, forming OH. So it's just the idea that water can be an acid or a base. Again, we're understanding that better, that things that are acidic because they're more acidic than water. Things that are basic because they're more basic than water. But water can form either function. And so there's a name for that, and it's called amphoteric. So guys, amphoteric means a substance that can be acidic or basic, depending upon the other player. And by the way, guys, water is not the only amphoteric substance. There's lots of them. One that I'm really aware of is actually, see, I don't like green. No.
You're so boring.
I know. But I'm good at what I do. So guys, HSO4 is actually another amphoteric substance. If you put this with a base, it will give away a hydrogen and turn into sulfate. If you put it with an acid, it will actually accept a hydrogen and become H2SO4. And the reason this is interesting to me is it's actually the salt. It's actually sodium bisulfate. This is actually the stuff that they use to buffer swimming pools and hot tubs. You put this in a hot tub, and it actually will initially drop the pH because it's good at giving hydrogens, pretty good at giving hydrogens away to water. But once it's in solution, it can also take in hydrogens from water, and it functions as both, and we'll talk more about that later. But sodium bisulfate is one of the salts that you use to maintain swimming pools and hot tubs. So there you have it. You okay with amphoteric? Okay, let's go here. This is interesting. Guys, Luke asked, and you're going to have an aha moment here. This is pretty good. Let's do this. Guys, what's the pH of water? 7. Keep that in mind. Okay, so guys, this is what is called the autoionization of water. So Luke asked the question, what if water takes a hydrogen away from water? Well, guys, now that we understand that water is amphoteric, we understand that water can give or take hydrogens. So guys, what if they get together just in a bucket of water? Well, what do? Well, guys, they do this. Water reacts with water. And when this happens, water can take hydrogens from water, and when they do, we end up with hydronium ion, and we end up with hydroxide ion being formed in the water. And guys, understand, this is not some crazy pie-in-the-sky idea. This happens. Yeah? Like a beaker, you know, when I bring out the big things of distilled water, there's nothing else in there but water, and this chemistry is taking place in the water. Now, guys, you'll notice that in this, are y'all on this page in the notes? You'll notice it asks you to write the Kc expression for this. Please do it. In that space, write the Kc for this. Do y'all get this? You okay? So guys, let's make sure we're clear on this. So the denominator of the fraction is H2 and H2, but H2 times H2 is H2 squared. Is that okay? You're all right? Okay, because guys, this is wrong. Good. Guys, this is a heterogeneous equilibrium. This is a liquid, this is a liquid, this is aqueous, this is aqueous. And guys, liquids and solids do not go in Kc expressions. So guys, what that means is that this denominator does not belong there, and this is actually what the Kc expression looks like. You okay? But guys, here's the trick. This is the Kc expression for the autoionization of water. And because that's the case, we do not call it Kc, we call it Kw. Find it on your equation sheet. Do y'all see it? You got it there? You're good? You sure? Because, guys, we're about to do something fascinating. Y'all find it on your paper? Okay, so, guys, the question is this. Why on earth is Kw important enough that it makes it onto the equation sheet? Guys, check this out. Ready? I've got some questions for you that are not in your notes. Join me up here. You're going to find this interesting. So, guys, it goes like this. I'm going to rewrite this. Kw is hydronium and hydroxide. So, guys, here's questions. Where does the hydronium and the hydroxide come from? From the water. Now, guys, think about this. If the hydronium and the hydroxide comes from the water, what do their concentrations have to be? Equal. Let that rattle in your brain for a minute. They have to be equal. Do you see why? Explain why. Why do they have to be equal? You said they come from water, but how do they form? Guys, follow the hydrogens. Look at the reactant side of the equation that's on the screen and follow the hydrogens. How does this go? Well, guys, let's say that there's a hydrogen that so water, here, let's do it this way. So, guys, water is HOH. Water is HOH. So let's say at any given moment, the left side hydrogen, the left side water functions as an acid. So this guy gives away its hydrogen. When that guy gives away its hydrogen, what does this become? OH. What does this become? H3O. But guys, does it make sense that for every one of these that's formed, one of those has got to be formed based on the very place that they come from? Does that make sense? You're good? Okay, so guys, are you sold on the idea that these concentrations are the same? You're good? Now, I'm going to tell you what the concentration is. And guys, would you expect the concentration of these two ions to be high or low? Pretty low, right? You jump into a bucket of water and it's not like, oh, it's an acid, it's killing me. Guys, it's water. So these concentrations are not only equal, don't take your eye off this, they're not only equal, they're small. How small are they? They are both equal to 1 times 10 to the negative 7th molar at room temperature. You having the aha moment? Guys, what's the pH of water? 7. This is why. pH is the negative log of hydronium ion concentration, right? pH is the negative log of hydronium ion concentration, and if you plug in, that's not a 1, that's a 7, and I underlined. Guys, if you plug in 1 times 10 to the negative 7th into that equation, then guys, the answer is 7. That is why pure water has a pH of 7, because the molarity of hydronium ion in that solution at room temperature is 1 times 10 to the negative 7th. Do you see it? But now, guys, here's an additional interest. Are you guys sold on this? Here comes an interesting additional thought. Guys, let's go to the next page. Looks like this. So we now know these values. 1 times 10 to the negative 7th, 1 times 10 to the negative 7th. When we plug in those numbers, what is Kw? 1 times 10 to the negative 14th. Look on your equation sheet. Do y'all see that? It's given to you. Or at least it was 2 years ago. Is it still? Hold on, let me catch up with you. Where's it at? Oh, there we go. Oh, good, good, good. Okay, so guys, Kw is H, and it's right there. 1 times 10 to the negative 14th. But now, guys, join me because this is interesting. Why? Why do we care about this stupid equation? And guys, the answer is this. Ready? You could even draw this with me if you want. Let's draw a bucket. And inside this bucket, we've got some water. And inside this water, can I just drop the times 1 times? If I just do this, forgive me for my, well, I can do better than that. Not much better, but, oh. Is that okay? Okay. So guys, this is what's going on inside a bucket of water at room temperature. Why do I keep saying room temperature? Because you understand that equilibria shift based upon temperature. If we knew if this process were endo or exothermic, we could figure out what would happen to these molarities as we increased or decreased temperature, but I don't know and we're not going to worry about it. We're always going to say room temperature. But guys, here's the deal. At room temperature, this is 10 to the negative 7th molar, this is 10 to the negative 7th molar, this is 10 to the negative 14th. Now guys, here's the scoop. So long as we don't change temperature, what happens to the value of Kw? Nothing. It doesn't change. Remember how in the previous unit we established that the only way to change the value of Kw is to change the temperature? We good on that? Because guys, this is where this is about to get important. Join me. Here's the idea. Are you guys all sold on the idea that Kw doesn't change? Now watch this. Let's add, I'm going to switch colors. Let's add an acid. We're going to add an acid to this water. We're not going to get into the chemistry yet, but we are going to look at the math. Guys, when we dump acid into this water, which molarity changes? Acid is a source of what? Hydrogen ions. So guys, when we add this acid, what we're really adding is hydrogen ions. As we add hydrogen ions, what's going to happen to the concentration of hydrogen ion? It's going to go up, right? Dumping in hydrogen ions makes the molarity of hydrogen ions go up. But now guys, check this out. If the concentration of hydrogen ions goes up, and if Kw doesn't change because it's a constant, what has to happen to the concentration of hydroxide? It's got to go down. And guys, that's the magic of this Kw equation. That if we know the concentration of hydrogen ion, hydronium, if we know the concentration of hydrogen ion, we can then figure out the concentration of hydroxide ion for any solution because Kw doesn't change. So if there's nothing else in there but water, they'll both be 7, 10 to the negative 7. But if we add acid, hydronium goes up, hydroxide goes down. If we add base, hydroxide goes up, hydroxide goes up, hydronium goes down. But they will always multiply together to give you 10 to the negative 14th. Do you see how that works? So guys, that's the power of this Kw equation, is if we know one, we can solve for the other at any set of molarities. You guys good on the idea? So where does that put us then in the notes? So let's do this. So then guys, the question, and so I think we're good on that slide. Let's go to the next slide. So then, guys, the question becomes, how do we figure out these values for the concentration of hydrogen or hydronium? And the answer is pH. This is how we figure out the molarities, is we simply measure the pH. And guys, notice that this is in 2 forms. It could be written as hydrogen ion. It could be written as hydronium ion. We've already agreed we understand those are the same. The only difference is one we include the water, the other we don't. But guys, this equation allows us to figure out hydrogen and hydronium ion concentrations. Do we need to solve this, or do you know how? Are we okay? There will be a little practice in the homework if you need to look at it. But you guys okay? You okay with the math? Then guys, let's get into this interesting thought. Look at the next page, and I'm going to zoom into it. So here we have a pH scale. Let me get in writing position. So guys, this is interesting. So here we have a pH scale. But you'll notice across, and I would encourage you to doctor this up. These are big ideas. So guys, look at what we've got here. Let's start with the stuff that's familiar. pH. So let's be clear. Guys, pH 7 is neutral, right? Which then are the acids, the higher the low numbers? The low numbers. So the lower the number, the stronger the acid. And then guys, anything above pH, above 7 is understood to be basic. So guys, let's start with the familiar. Stomach acid, pH 1. Guys, good night. pH 1, right? Your gut is full of pH 1 hydrochloric acid. So what does that mean when we hear that it's pH 1? Well, guys, what it means is this. It's 1 times 10 to the negative first molar hydrochloric acid. This one is that one. That's how logarithms work. That's the exponent. So guys, written out, this is 0.1, written in decimal form. It's 0.1 molar of acid. Now guys, let's do lemon juice, which is pH 2. That's less acidic, right? pH 2 is less acidic than pH 1. So what does it mean? Well, that's 1 times 10 to the negative second molar. But guys, if you write that out in decimal form, it's 0.01 molar. Do you now see why it's less acidic? Is that okay? The idea, guys, that these numbers are the exponents, but because they are negative exponents, it's actually making the decimal smaller. So when you get up here to something like coffee, it's acidic. It's pH 5. What that means is 0.00001 molar, which is 1 times 10 to the negative fifth molar. You get the idea? Okay, but now guys, watch this. This tells us, the pH tells us the concentration of hydrogen. But guys, it turns out that in these solutions, we can also talk about the concentration of hydroxide. So guys, let's go down to our original solution, the stomach acid, and now let's talk about hydroxide concentration. So guys, now we've got 1 molar, which is 1 pH was 10 to the negative first molar of hydrogen. But guys, look at how small the concentration of hydroxide is. 1 times 10 to the negative 13th. But what do those two numbers multiply to give you? 1 times 10 to the negative 14th, which is Kw. And guys, that's the point, that Kw is equal to hydrogen times hydroxide. So as the hydrogen ion concentration gets smaller, the hydroxide ion concentration gets bigger. They work inversely, pivoting around Kw, which is the fixed point, 1 times 10 to the negative 7th. So guys, the idea then is this. Here's pure water. The pH is 7, and notice this idea. The pOH. Do you see it on the equation sheet? Do you guys see the pOH equation on there too? So you've got pH is negative log of H plus, and then next to the pOH is the negative log of hydronium ion. New idea, but guys, it's still the same math. So we've got the pOH, which tells us this is 10 to the negative 7. We've got the pH, which tells us that is 10 to the negative 7. And notice, guys, they multiply together 10 to the negative 14. And here they're equal. That's water. But now we get into the bases. So guys, let's go to household bleach. And let's say household bleach is pH 12. So guys, pH 12 means this is 1 times 10 to the negative 12. But now conversely, the hydroxide ion concentration is 1 times 10 to the negative second. Again, those multiply to 1 times 10 to the negative 14. That's pOH of 2. And we can do all of these interplays throughout all of these relationships with pH, pOH, hydrogen ion, hydronium ion. It's all over the hydroxide ion, and all of these relationships hold true throughout the entire table. Go ahead. Absolutely, yeah. Yeah, so for example, let's just do this. the acid that you guys used in lab today, right? It was 0.5 molar HCl. So that would be the negative log of 0.5. And if you do that math, where do I go here? So that, oh wait, no, I'm sorry. That's not a good example. That would have a pH of 0.301. But exactly. So let's, yes, you're right. I'm sorry. So we've done labs where we've used 6 molar hydrochloric acid, right? And if you go 6 and do the math on that, it's actually, so 6 molar hydrochloric acid, if this were a 6, the pH of that would be negative 0.778. Yeah, so definitely you can. So when we say the pH scale ranges from 1 to 14, that's biologically. Those are the pHs that we see in nature. Yeah, we can, the pH scale actually does have an upper and lower bounds, and I forget what it is. I think the lower bounds is like negative 1.8, and the upper bounds is somewhere in the 16s. So, yeah.
So when you do go above, when you do go below a pH of 1, what happens to the pH?
Yeah, it keeps getting smaller and smaller and smaller. Yeah, yeah. Is that okay? We okay? So, guys, this then brings us to an interesting thought. Staying on this page, check this out. So, guys, if you haven't been writing anything else into this table, I would encourage you to do this, because this is interesting. So here we have pH, and here we have POH. And then, guys, here we have hydrogen and hydroxide ion concentrations. And, guys, you understand that these are related, right? I'm going to have to write really small to make this fit, but let's talk about all the relationships. So, guys, how is pH related to hydrogen ion concentration? pH is equal to the negative log. Is that okay? I know it's small, but you know what I'm writing down. Then, guys, what is the relationship between POH and hydroxide? Same thing. POH is equal to the negative log of hydroxide. But now, guys, we've got some bigger relationships to talk about. And it goes like this. How are hydrogen and hydroxide how are those molarities related? They multiply to give you Kw. So maybe you just write Kw right there, and off to the side you remind yourself that Kw is hydrogen times hydroxide. But guys, there's one more relationship, and we haven't talked about it, but I wonder if you see it. It's this relationship. The relationship between pH and POH. And guys, we're not going to get into the math, but this reality and this reality, when munched together with this reality, gives us a whole nother interesting reality, which is the relationship between these two. And what is the relationship? Do you see it? Just allow your eye to scan down the two outside columns. They always add up to 14. Guys, the pH, 14 and 0, 13 and 1, 12 and 2, 11 and 3, 3 and 11. Guys, the pH plus the POH, and again, I don't know how to make this stand out, always adds up to 14. And guys, if you're I don't know better, if you're bright mathematically, forgive me, that's horrible, but if you can't see this, it doesn't mean you're not bright, because I don't see it. But guys, this reality that pH plus POH is 14 is actually based upon this. If you plug in 1 times 10 to the negative 14th for Kw, and then if you take the negative log of all of them, this ends up being 14, this ends up being pH, this ends up being POH, and that's another reflexive thing that we can use. And you'll notice that it's also on the equation sheet. See where it says 14 is equal to pH plus POH? Okay, so guys, basically what we've done is we have set an amazingly interrelated set of groundwork. We've understood the idea that acids give away hydrogens, bases take them in. Then we talked about the idea that water is no longer passive. Water gets involved in the chemistry. And then we did all of this amazing, crazy stuff relating concentrations of hydrogen, concentrations of hydroxides, the way those interplay as we add acids and bases to the water. And guys, as you get into this homework today, there's the possibility you're going to get spun around because you're going to be like, oh my gosh, all of these different relationships. Guys, take the time to work through it. You're going to find that these relationships really do settle out as we get deeper into this unit. But for now, you just have to do the work and work your way through these things. Before we finish, however, there's one last thing that we need to talk about. And this is going to make great sense, but we do need to talk about it. And it's this. Guys, when we talk about, just read this with, very last slide. When we talk about strong acids and bases, and guys, I would encourage you to circle the word strong. When we talk about strong acids and bases, what does strong mean? Complete. Now guys, just read what it says. In the case of strong acids or bases, we consider the concentration of the acid to equal the concentration of hydronium ion. Guys, let me show you what that means. You could write this down. 1 molar HCl. Imagine that you have a bucket of 1 molar HCl. How much HCl is in that bucket? It's not a trick question. If you have 1 molar HCl, how much HCl is in that bucket? None. Right? Where does the water go? Or I'm sorry, where does the HCl go? It forms hydronium ion and it forms chloride ion. And guys, what are the concentrations of those in a 1 molar solution? 1 molar this and 1 molar that. Okay? Now guys, do this. 1 molar acetic acid. How much acetic acid is in that bucket? A lot. More than 99%. We'll do the math later. Guys, there's a lot. The reason is because this reaches equilibrium with its parts. So you've got all 3 of those species in water. Now let's talk about molarities. What is the molarity of the acetic acid? But it's less than 1, right? So we know that this will be less than 1 molar. What will the molarities of these be? Well, more than 0, right? But how much more than 0? No. How much more than 0? The same as the amount that this went down from 1. Guys, let's say that again. What will the molarities of these be? The same as the amount that went down from 1. Now guys, why is it important you understand that? We just did an icebox. Do you see it? How much did this go down? The same that those went up. What are we going to do on Monday? That. We are going to apply ice boxes to weak acids and bases. Now guys, before we do though, this is important for your homework today. When we're talking about strong acids and bases, the concentration of the acid is the concentration of hydronium ion. In a weak acid, the concentration of the weak acid is not the concentration of the hydronium ion because not all of the acid breaks apart. Do you see? So guys, this you're going to see in homework today. This we're going to talk about when I see you on Monday. You guys good? That's a lot of stuff, isn't it? But it's interesting. So guys, homework is there in front of you. And I'm going to be honest with you. It's as big as it looks. So guys, let's just say this now. I will protect you as much as I can from doing unnecessary homework. I hope at this point that I've earned your trust, that I'm not just laying homework on you for the sake of laying homework on you. And guys, I think I'd be curious to know if you agree. Have you been surprised at how little homework you do in an AP Chem class? And really I want to know. But guys, I typically, and I've never asked you guys this question, typically people at this point in the year say, man, I was expecting this to be a lot more work. Not hard, but a lot more just hours of homework than it's turned out to be. Maybe. And that's possible, maybe. But guys, I'm just going to be straight with you. The amount of homework is going to increase, at least for the next couple days. There's no way around it. This is dense material. But guys, rise to the challenge, schedule time, get the homework done. Guys, we've got a minute left. I need to stop recording before I forget.